Hi there, this is Mr. Schnitzius, and in this video we're going to finish activity 34. Our learning targets in this video are still going to involve prisms and cylinders, but this time we're going to find the volume of both a prism and a cylinder. Let's look at how to do it. Extreme Exteriors gives their tour guides a thermos before every excursion. Depending on the excursion, the thermos is either a right or an oblique cylinder. Sometimes the thermos is easier to carry on a bike or in a kayak if it is oblique. Inside each thermos is a small filter in the shape of a hexagon, which uses thin hexagonal-shaped filter paper. Extreme Exteriors always keeps a container of filter papers on hand. Examine the filter paper container shown. The base of the container is congruent to each filter paper. So we're first going to name the figure that describes this container, and that's going to be a hexagonal prism. It's a prism because the lateral faces are all rectangles, and it's hexagonal because it has a hexagonal base, a polygon with 1, 2, 3, 4, 5, 6 sides. If the area of each filter paper is B, they want to write a formula that finds the volume of filter paper that the container holds. Well, that would be the area of the base times the height. This gives us the area of one paper times the height, helps to account for how many pieces of paper we can hold in there. So now for number 3, it says, suppose the radius of the container is 2 inches and its height is 4 inches. So let's label that height 4 inches. Let's put the radius here as 2 inches. So they want us to explain what is the volume of filter papers that fits inside the container. And they want us to explain how we arrived at our answer. Well, it says the hexagon is divided into 6 equilateral triangles. So let's try to see why that is. If we draw all these radii of the hexagon, we end up with 1, 2, 3, 4, 5, 6 triangles. Why are they equilateral? Well, because if this point is the center, then all these radii are going to be exactly the same. They're all going to be 2 inches long. So it also says that each equilateral triangle can be divided into 2 30, 60, 90 triangles. So let's draw that out. Here's one of the equilateral triangles, 2 inches for the length of every side. And they're also telling us that we get 2 30, 60, 90 triangles when we split this in half. Why is that? Well, because if all 3 sides are congruent, all 3 angles have to be congruent. So when we divide this equilateral triangle in 2, we end up with a 30 degree, 60 degree, 90 degree triangle. 90 degrees because that's a right angle, 60 degrees because we started out with 3 60 degree angles, and 30 degrees because that top 60 degree angle is bisected, split in 2. So if this hypotenuse is 2 inches, well, then we should think about how we label the sides of a 30, 60, 90 triangle. Across from the hypotenuse is a side length labeled 2x. Across from the 60 degree angle is a side length labeled x times the square root of 3. And across from the 30 degree angle is a side labeled x. Well, this is about as easy as we could hope for. If 2 inches is equal to 2x, then that means that x must be 1 inch. And the height must be 1 times the square root of 3 inches. So now it's telling us that since the radius is 2 inches, the legs of the right triangle are 1 times the square root of 3. That's the apothem. That's one leg, and the other leg is 1 inch. That's the side that we solve for right here. That gives us the base of the hexagonal prism. So let's actually solve for that base area. The area of the base is going to be 6. Why is that? Because we've got 6 congruent equilateral triangles right there. It's going to be times the area for one triangle, so that's 1/2 times the base. Remember, the base is the full 2 inches, times the height, which is the square root of 3. So if we work that all the way out, 1/2 times 2 is 1. So that's going to be 6 times the square root of 3 inches. They showed a little extra step here because 1 plus 1 is how we got the 2 inches for this entire length along the bottom. So if we want to get the volume, we just need to multiply this base area times the height. So 6 times the square root of 3 times 4 for the height gives us a total volume of 24 times the square root of 3 inches cubed. Now in part B, it says a new container is created in which the radius is tripled and the height remains the same. Describe how the change in dimension affects the volume of the papers that fits the containers. Well, if the radius of the new container is 6 inches and the height is 4 inches, that gives us an area for the new hexagonal base of 54 times the square root of 3 square inches. So let's see how they got that. Now, if the radius is 6 inches, let's go back and look at how we got this area for the base, right? We still have 6 congruent equilateral triangles, but now it's going to change how we set up our 30, 60, 90 triangle. See, now when we set this up, it's still a 30-degree angle there and a 60-degree angle at the bottom. But if this length is 6 inches and that's a length of 2x, well, now our x is going to be 3 inches, and our x times the square root of 3 is going to be 3 times the square root of 3 inches. So that base area now is going to be 6, because there's 6 congruent equilateral triangles in there, times 1/2 times the whole base, which is 6 inches, times the height, which is 3 times the square root of 3 inches. So that 6 times 6 is how they got 36. There's the 1/2 from the area formula. There's the height of the triangle. So that's how we end up with 54 times the square root of 3 inches squared. So since the area of the new base is 9 times the area of the original base and the height stayed the same, the volume of the new prism will be 9 times bigger than the original prism. So now we're going to talk about Cavaliers Principle. Cavaliers Principle states that if two solids lying between two parallel planes have the same height and all cross sections at equal distances from the bases have the same areas, then the solids have the same volume. So we've got two cylindrical shaped thermoses with radius r and height h. Basically, what this principle is saying is if the height is the same, as long as each of the cross sections at each distance above the bottom give us the same area, then that guarantees that the volumes are going to be the same. So it says, suppose a plane parallel to the base of the cylinder passes through the cylinder. And they want us to describe the cross-section of each cylinder. So I've got a way that we can see that. Here's a cylinder. And if we put a plane parallel to the base of the cylinder, let's see what we end up with as the cross-section. That means the view that we get whenever we look at what would be left over from the top when we cut off the part that the plane sliced. Well, that's a circle. So the cross-sections for both cylinders would be congruent circles. And what is the area of the cross-section for each cylinder? Well, the area for a circle is pi r squared. So number 5 says, recall the volume formula for a prism in item 2, where capital B is the base area and h is the height. What is the base area of the cylinder? How does this compare to your answer in number 4, part B? Well, it's still pi r squared. That gives you the exact same circular area. So if each cylinder was dissected into wedges and rearranged to form a solid like that of a prism, well, we know that for the volume of a prism, we do the area of the base times the height. So that means that the volume formula for a cylinder is going to be capital B times h. And since the capital B is the area of a circle, the area of a circle is pi r squared. That gives us the volume formula. The volume equals pi r squared times the height. So here's an example that we can solve out. The volume of the cylinder shown is 450 cubic feet. The diameter is 8 feet. What is the height of the cylinder? Well, all we need to do is use this volume formula. And if we can work that backwards, we should be able to solve for what we need. So they rearranged the equation before they plugged anything in. So that's V equals pi r squared times h. They want to get h by itself, so they divided both sides by pi r squared. So they got the height is the volume divided by pi times the radius squared. And then when they plugged in 4 for the radius and 450 for the height, they got about 8.95 feet. So we're going to use that to solve 3 examples on the try these A at the bottom of page 501. The first one says the volume of a cylinder is 220 centimeters cubed and the radius is 5 centimeters. What is the height of the cylinder to the nearest tenth? Well, we can actually just use this same formula right here. We already showed the work to see that if you're solving for the height, that's equal to the volume divided by pi times the radius squared. So we're going to write that out. So they told us that the volume is 220 cubic centimeters divided by pi times 5 centimeters squared. So when we work that out, put that in your calculator, you should get about 2.8 centimeters. Not too bad. Okay, this one is giving us some different information. The volume of a cylinder is 90 meters cubed, and the circumference of one of the bases is 27 meters. Well, if we know that the circumference is 27 meters, and we know that we can use the circumference formula 2 times pi times the radius, well, if the circumference is 27 meters, and that's equal to just 2 pi r, sorry, that should be 27 equals 2 times pi times r. We can use that to solve for the radius. When we divide both sides by 2 pi, now we're going to get that the radius is 27 divided by 2 pi. All right, so what does 27 divided by 2 pi come out to be? Rounded to the nearest tenth, that's going to be about 4.3. meters. So now if we're trying to solve for the height of the cylinder, we can do the same thing that we had right here. The height is the volume divided by pi r squared. Well, we know that the volume is 90 cubic meters. We know that the radius now is about 4.3 meters, and we're squaring that. And whenever we work that out in the calculator, we're going to come to the height is 1.55 approximately meters. All right, one last example. The volume of a rectangular prism. So we need to ditch this picture, sorry. The volume of a rectangular prism is 120 feet. The width is 15 feet and the height is 4 feet. What is the length of the prism? Well, if we draw this out, when I draw a rectangular prism, I like to draw two congruent rectangles, one in front of the other, and then connect them, except really connect them about like this. So they're saying that the height is 4 feet. They're saying that the width is 15 feet, and they want to know the length of the prism. Well, we know that the volume formula for a prism is the area of the base times the height. But since the base is a rectangle, we can say that the base is length times width. So we're just going to work backwards from this formula. We know that the volume is 120 cubic feet. We know that that's equal to the length, which we're trying to solve for, times the width of 15 feet, times the height of 4 feet. So if we work this out, 120 cubic feet equals 15 feet times 4 feet is 60 square feet times the length. And when we divide both sides by 60 square feet, 120 divided by 60 is 2, so that's going to give us a length of 2 feet. So we've got another problem here. The volume of a rectangular prism is 480 cubic feet. There are many possible dimensions for this prism. We just need three numbers that we can multiply together to get 480. So their idea is 6 feet by 8 feet by 10 feet. So we can label that here 10 feet, and maybe this is 8 feet, and maybe this on the bottom is 6 feet. So now it's saying if the dimensions of the base are doubled and the height remains the same to create a new prism, what will be the volume of the new rectangular prism in cubic feet? Well, let's just say that this prism is sitting on its side, so let's say that the height here is 10 feet. If the dimensions of the base are doubled, that would mean this 8-foot length is doubled to be 16 feet now. This 6-foot length is doubled to be 12 feet now. But if the height stays the same, then this height would still be 10 feet. So the new volume would be, well, the length, 12 feet, times the width, 16 feet, times the height, 10 feet. And then if you multiply that all together, that gives you 1,920 cubic feet. So describe how the change in dimensions affects the volume of the prism. Well, the volume is multiplied times 4. And if you want to see why that is, that's simply 1,920 divided by 480 is what gives us an area ratio of 4. So now we're going to do some comparing volumes for cylinders with volumes of prisms. Brooke is looking to purchase one of two new styles of tints. One tint is in the shape of a half cylinder and one is in the shape of a triangular prism. Since the price of the tints is dependent on the area of material, Brooke wants to find the tint with the greatest volume using the least amount of material. So we're going to go through this multi-step problem just a little bit at a time. So we're going to find the volume of each tint. First, we're going to do the volume formula for a cylinder. So that's the area of the base times the height, which is pi r squared times the height. But this is not a full cylinder. This is only the top half of the cylinder. So we're going to multiply that total that total volume of the cylinder times 1/2. Okay, so if we go through and find the volume for tint A, it looks like the radius is 3 feet. They're showing us that here. So it's going to be 1/2 times pi times 3 squared times the height. The distance from base to base would be 8 feet. So that's approximately 113.1 cubic feet. Now we're going to look at tint B. What is the figure that describes the base of tint B? Well, that is not just a triangle, but an isosceles triangle. Let's think about how they got an area of 15 square feet. The area for a triangle is 1/2 times the base times the height. So that's going to be 1/2 times the base of 5 feet times the height of 6 feet. So 5 times 6 is 30, and 1/2 of 30 is how we get 15 square feet. So if we want to get the volume for this tint, that volume formula is going to be the area of the base. Well, hey, that's handy. We already worked that out up here. Times the height. They got a height of 7 feet. That's the distance from base to base. And so that total volume for tint B is 105 cubic feet. So if we want to know which tint has the greater volume, that would be tint A, because this volume of 113 cubic feet is larger than the volume of 105 cubic feet. Now we're going to compare the surface areas for each tint. And we want to remember that each tint has a floor. So for the shapes that describe the base and the lateral faces of tint A, well, we've got rectangles and we've also got semicircles. So if the total surface area is the lateral area plus 2 times the area of the base, in this case that would be 2 pi RH plus 2 RH plus 2 pi r squared. So if we're going to do this for part, now where does this RH come from? 2r is this length 6 feet. If the radius is 3 feet, then double that is 6 feet. Okay, and then this length of 8 foot is the height. But for tint A, we only need the area of one base. Why is that? Because we've got one semicircle here plus another semicircle over here. We're also doing only the top half of the lateral area, so that's why we changed this 2 pi RH, the lateral area for a cylinder, to just pi RH, the lateral area for tint A. So when we plug into this formula, substituting 3 feet everywhere we see R and 8 feet everywhere we see H, pi times 3 times 8 plus 2 times 3 times 8 plus pi times 3 squared gives us approximately 151.67 square feet. Now we're going to look at tint B. So what shapes describe the base and the faces of tint B? Well, we've got two isosceles triangles that we already found the area of. Two isosceles triangles with sides of 5 feet and 6.5 feet. So let's look at how they got the 6.5 foot lengths right here. Well, as you can see, this height, 6 feet, is perpendicular to the base of 5 feet. So that gives us a right triangle. So we know that this height is 6 feet. This height is a perpendicular bisector, so that's going to be 2.5 feet, and we're looking for this side C. So right triangle, we can do Pythagorean theorem, 2.5 squared plus 6 squared equals C squared. So that is 6.25 plus 36 equals C squared. The square of the hypotenuse is 42.25, and when we take the square root of both sides, that gives us the length of the hypotenuse. That's 6.5 feet. So since that's an isosceles triangle, that's the same on both sides. So, but we've also got a rectangle on the bottom that's 7 feet by 5 feet. And we've got two rectangles that are 6.5 feet by 7 feet. So if we want to find the surface area for tent B, that's going to be the lateral surface area, the perimeter of the base times the height, plus 2 times the area of the base. Well, that's going to be a height of 7 feet. They got the perimeter of the isosceles triangle base by adding 5 plus 2 6.5 foot lengths. So that's how they got that 18 feet. So the surface area for tent B, this 18 feet times 7 represents the lateral surface area, plus 2 times the area of the triangular base. So if you work that out, you get 156 square feet, which means that tent B has a greater surface area of 156 square feet compared to tent A. So here is a comparison of the volumes and surface areas for the two tents. Which tent has the greatest volume with the least amount of material? Well, tent A has larger volume and less material. So, and you could work that out by comparing ratios. 113.1 divided by 151 is going to be larger than 105 divided by 156. So that means that the winner, the tent that she would want to buy, would be tent A. All right, lastly, we're going to solve some check your understanding problems. So number 10 says in number 8 and number 9, why are the units for perimeter, surface area, and volume different? Well, perimeter is a linear measure, meaning that's only measuring how long the distance is. So it's going to be measured just in plain units. Surface area is a measure of the number of square units. So that's why it's measured in square units. Whereas volume is the number of cubic units that can fit into a figure, so it's going to be measured in cubic units. Number 11, true or false? If a right prism and an oblique prism have congruent bases, then the volume of the right prism can never be equal to the volume of the oblique prism. If true, state the theorem that supports this fact. If false, provide proof. Well, this is false. And the reason why is if the heights of two prisms are the same, then the volumes will be equal. So just to remind us of that, here's another picture of Cavaliers Principle. Just imagine this shape, instead of being a circular base, is a, this could be a square here that's congruent to a square here, or a triangle here that's congruent to a triangle here on the top and on the bottom. As long as the heights of the two prisms are the same, and as long as all cross sections at equal distances from the bases have the same area, you're guaranteed that the solids will have the same volume. All right, lastly, number 12 says if a cylindrical container does not have a lid, does it have an effect on the measure of the volume, the surface area, neither, or both? Well, if you don't have a lid, that's going to affect the surface area. One common way to think about surface area is if you take the three-dimensional object and you are trying to calculate how much paint you would need to paint the outside, that's a surface area calculation. Well, painting a cylinder with a top on it is different than painting a cylinder without a top on it. However, the volume does not depend on the top face or the base of a figure. The surface area does, however. So if one of the faces is removed, then the measure of the surface area decreases. Okay, that's it for activity 34. Thank you guys so much for your hard work.